just like to say Mr. Evans is the greatest high school teacher ever, and that throughout my... What? This isn't helping my grade at all? Oh. Alright. Roll the intro. Hey! Welcome everybody. You are watching the very first Things Like Chemistry with Joey Pacheco. So check this out. Today, we're going to run through the gas laws. Alright? And the first three we're going to run through are going to be Boyle's Law, Charles' Law, and Gay-Lussac's Law. These are pretty basic. They all just have to do with pressure, temperature, and volume, and how they relate to each other inversely or directly. Alright? So to start us off, let's check out Boyle's Law. So as you can see, as the man blows into the balloon, the volume increases, as does the pressure, until such a point when the container can no longer contain it. We'll start with Boyle's Law, which states that the volume and the pressure of a gas relate inversely to each other. This means that if volume increases, then pressure will decrease. However, if volume decreases, then pressure will increase. Now we can all see I have this beautiful Nerf gun here. Alright, pretty standard. Just got this ball inside of a giant tube. Just one ball. Oh my gosh! The ball is green, so you can't see it. Whoops. Okay, there's a ball here. Here, see? It's in front of my face now. Now you can see it. There's a ball here, okay? Sorry about that, guys. Actually, I wonder if you can see the Nerf gun, because some of it's green, too. Anyways. I digress. Here, it is in open position. Therefore, we have volume of the gas inside the tube. Alright? However, when I pull this back, the volume is decreasing and the pressure is increasing. And when pressure builds up enough, the ball will explode. Our second law is Charles' Law, which states that volume and pressure are directly related, which means that as one increases, so will the other. But as one decreases, so will the other. I got a few friends that are going to show you what I'm talking about.
This is the Charles' Law Lab, Chemistry 1B. Nice.
What's the law? I'm confused. Explain what we're doing here.
The air is expanding when it is boiling, and when you set in the cold water, the air contracts, and there's very little pressure inside the can, and the atmospheric pressure is stronger, so it crushes the can.
Get out of town. No way.
No, it's fine.
Alright, here we go. You ready?
Moment of truth. Let's see it. Try speed jump.
Oh my gosh, the can just crushed up to nothing.
Maybe even broke.
And there you have it. Pick up the can once. Feel kind of what?
Heavy because the water's sucked up inside of there.
Exactly.
Crazy.
Alright, good deal.
Smile, John.
So wait, what just happened? As the temperature increased, so did the pressure. So the bag shriveled up. Is it just me? Or did the pressure increase just as you walked in? Weirdo. But what he says makes a lot of sense, because our third law is Gay-Lussac's law. And this states that as the pressure increases, so does the temperature. And as the temperature decreases, so does pressure. So check this out. Those guys.
Okay, we've got some liquid nitrogen, which is minus 196 degrees. Let's see what happens if we put that over an air-filled balloon. So the air's got really cold inside. Air, when it gets cold, gets smaller and falls down. Let's warm it up using the breath from my lungs.
Working with nitrous gas. That's always cool. So, one more time. The balloon was super cooled. He said, nitrous gas. I mean, that's some cold stuff right there. So it was super cooled, and you could tell. Small balloon. Alright? And I mean, then, the guy breathes on it. So that's some hot breath right there. Alright? Some hot breath. And it inflated a little bit. Which that is a testimony to how cold the nitrous acid is. That's some beastly science right there. That's, yeah. No, stop moving the camera. No, I'm talking. I'm talking. Hey! Alright. We will check out the combined gas law and the ideal gas law right after some words from our sponsors. Weird Al Yankovic. Weird Al Yankovic. That was an explosion. Just like what just happened to your mind if you think you're going to memorize each one of those guys, each one of their formulas, and how to convert all that and everything. And it's what happened to scientists in the 1800s, or whenever they discovered this. So, they came up with the combined gas law. Cheat sheet. And the combined gas law states that pressure times volume divided by temperature is equal to pressure 2 times volume 2 divided by pressure 2. Which makes sense. And finally, we have the ideal gas law. Alright? Now, gases are weird and pretty much unpredictable. So, we need this thing that if gases were predictable, that we could calculate them with. So we have the ideal gas. Alright? real gases are not ideal, so they're different. But with ideal gases, we can predict and calculate what the outcome will be. Now, by calculate, I mean, I just dropped some papers. By calculate, I mean this formula right here in my book that I'm looking off of right now. You have to use the ideal gas constant, R. Pirates. No! Ninjas. I feel like I'm getting off topic. R equals P times V divided by T times N, whereas P is pressure and V is volume and T is temperature and N somehow ended up standing for moles. And R is your ideal gas constant, which is equivalent to 8.31. So the chemistry book has spoken. Check it.
PV equals NRGE. If the gas is ideal, that's the way it'll be. If the gas is ideal, that's the way it'll be. PV equals NRGE. If the gas is ideal, that's the way it'll be. If the gas is ideal, that's the way it'll be.
No, I'm not the chem student that I used to be. Got it all down now, Tommy, can't you see? A PV equals NRG. It's all that I want, so just store geometry. It's all you need.